Good morning. We are talking about the torsional formula. Last time that we derived the torsional formula based on the kinematical compatibility and then constitutive relation. So if we summarize the kinematical compatibility in terms of maximum shear strain on the surface of a circular section, it is given by the change of angle of twist and then the ratio between the radius of the cross section from the center to the top surface divided by the length of the segment. And then the constitutive relation is given by the Hooke's law for the shear stress and shear strain, engineering shear strain. The maximum shear stress is proportional to the maximum engineering shear strain, but the proportional coefficient is equal to the shear modulus. That was the constitutive law. And then equilibrium equation is given by this equation, which is a relation between the torsional moment. Make sure that this is the internal torsional moment, and then this is the maximum shear stress. So we can combine all these three equations together successively. For example, we plug the maximum engineering shear strain from the first equation to the second equation. And then the maximum shear stress in the second equation should be plugged into the third equation. Then if you combine all these three equations, we can obtain a formula for the torsional moment in terms of the change of angle twist between two ends of the segment, and then material properties and the sectional properties, and then the length of the section, isn't it right? So if you look at this formula carefully, alright, so let's take a look at this formula. The internal torsional moment is equal to the shear modulus, and then the polar moment of inertia divided by the length of the segment under consideration, and then multiplied by the change of angle of twist of the cross section, isn't it? But let's compare this equation with the actual load in one-dimensional loaded members. Internal actual force is equal to the elastic modulus times the cross-sectional area divided by the length of the segment, and then should be multiplied by the elongation of the segment, isn't it? So if you compare these two equations carefully, so you can find they are very similar to each other. For example, we have, in the sense of the kinematical description of the deformation is what? In the case of the second equation, it was given by the length change, isn't it right? The elongation. Here we have the change in angle of twist, okay? And then how about the material property? Here it was given by the elastic modulus, but now we need to deal with the shear modulus. And then how about the length? So we handle the same length, okay? And then how about the sectional property? In the case of the actually loaded member, we use the cross-sectional area, and then here we use the polar moment of inertia here, isn't it right? And then here we have an internal moment and then internal torsional moment. Okay, if you compare these two equations closely, we can find these two equations are very close to each other, right? Do you have any question, right? So which means once you memorize this equation, second equation, and as we discussed in chapter 2, and then the equation for the torsional moment, so we can memorize this equation very easily. Okay, and this equation is called torsion formula, okay? And then here the coefficient between the change of angle of twist and the internal torsional moment, and this coefficient is called the torsional flexibility, and then the inverse of this torsional flexibility is called torsional stiffness, okay? So it's better to memorize. It's worth of memorizing. Alright, so now let's talk about the application of torsion formula to other section rather than the solid circular sections. So as I told you, please, do you remember the solid circular sections are only sections where we can use this formula without changing anything. Otherwise, there is some warping displacement. That's why the direct application should be very limited. But how about hollow sections? The hollow circular sections are like this, okay? So in that case, please make sure that all the section properties are given in terms of the polar moment of inertia. So polar moment of inertia is definition of polar moment of inertia is what? This definition is IP. Polar moment of inertia is integration of the square of the radius to a material point, and then we need to integrate the small material point, okay? Actually, it's mathematically given in this way, but to understand it physically closely better, maybe we want to write in this way, right? For example, okay, look at this. So to calculate polar moment of inertia, let's imagine that we have cross section, and then we consider a small area, and then we need to consider square of it, okay? So basically, we'd like to sum over rho square times dA, okay? That's what we want to do. And the summation is changed to the integration, okay? Rho square and dA, okay? That's how. But make sure that this is integration. Integration means, you know, there is positive integration, and also it can be there can be, you know, negative integration too. So for instance, in the case of hollow section, okay, look, the hollow section means, so we'd like to subtract, you know, from this bigger solid section, and then the smaller solid section. That's what we want to do. Then we can easily obtain the polar moment of inertia for this hollow section, isn't it, right? So here, by the definition, so if you look at the formula, the table is given in our textbook, so you can easily obtain this formula, isn't it, right? So this is the polar moment of inertia for the solid section, and then because, you know, by the nature of this integration, we need to subtract the polar moment of inertia of the smaller section, okay? That's why we have this formula, okay? So here, but what if we, okay, let's imagine that we have a pipe, okay, structural pipe. In the case of structural pipe, the thickness of the pipe is very small compared to the diameter of the cross section, isn't it, right? So in that case, rather than using this formula, the full equation, so we can consider some kind of simplification, yeah, approximation. So let's consider the, rather than, all right, so if maybe you want to memorize this equation, right? So, but let's talk about where this equation comes out, okay? Okay, so exact expression of polar moment of inertia for hollow section is given by pi over 32, and then d2 minus d2 force minus d1 force. But I told you that usually d2 is noted with diameter, reference diameter, isn't it, right? The outer diameter is usually used as a reference one. So d false, okay, d false, and the minus, and then usually we use the thickness, okay? So d minus 2 times of the thickness to represent, you know, the geometry of the section, isn't it, right? This is exactly the same as before. Okay, since we have a common terms d here, d, okay, so let's take out. So if you take out the d to the front of this equation, d false, 1 minus 2 t divided by the diameter false. Is it clear, right? So as a first approximation, maybe we can consider this, because thickness t is much smaller than the diameter, so which means t over d is approximately equal to 0. So from this point, so we can neglect this. Then what's going to happen? Then pi over 32 d false, 1 minus 1. Okay, then what does it mean? It is equal to 0, okay? So it's a trivial, okay? Which means my approximation is not good, okay? We don't want to have 0 value, okay? So this approximation is not correct. So then what do you do? So instead of that, so we need more terms, okay? We need more terms rather than this rough approximation. Okay. So what I want to do is here I'd like touch here a little bit more. Say I have 1 minus 2 t over d and then force. This is equal to what? So 1 minus t over d square, and then I have another square. The same, isn't it, right? Okay, so let's solve out for this. Then 1 minus 4 t over d, and then plus 4 t over d square, and then it's square. Okay, let's check the relative the size of these quantities. So this quantity is already small, isn't it? But square of this is extremely small. That's why we can drop. Okay, so if you do that, then it is approximate as what? 1 minus 4 t over d, and then it's square. Then this becomes 1 minus 8 t over d plus 16 t over d square. And by the same logic, this guy is small, and then square of small thing is extremely small. That's why we can drop it either. So finally, we have this is approximated as 1 minus 8t over d. Okay, so let's use this approximation in this place. Okay. So then if you do that, this is equal to pi over 32 d false, sorry, and then here minus 1 minus 1, then because we have minus and plus 8 t over d. So this cancels. So finally, pi over 32 d false times 8 t divided by d, thickness divided by d. So then it becomes pi over 4, and then the reference diameter to the power of 3 times thickness. This is the polar moment of inertia for a hollow section. Okay? Do you have any questions? So if you want, instead of using the outer diameter as the reference one, you may want to use the average diameter as a reference one. Try if you have the same result in your place. Okay, that would be very instructive. Do you have any question here? Any questions? Okay, so now let's talk about non-uniform torsion. So here, let's say we have two different cross sections, and here we have multiple torsional moments. Okay, then we'd like to subdivide the problems into small segments, in which the condition is homologous. Okay, homologous to each other. Then the total angle of change, total angle of twist is what? The sum of all the angle of twist from individual segment. Okay, individual segment. Then we can obtain the total measure of angle of twist. Clear? And then because we can use a torsional formula. Once we define the angle of twist of a segment is by delta pi, then we can obtain the internal torsional moment from this equation. This is the standard formula here. Look at this, the torsional formula. Isn't it, right? So then to calculate the total amount of angle of twist of the problem, so what you have to do is we just superpose all the contribution of angle of twist from individual segment. Okay, then finally we can obtain this. It's so simple, isn't it, right? So basic principle is exactly same as before, as we discussed in chapter 2. Okay, no difference, same. Now how about if the torsional moment is continuously distributed by a function? So even in this case, the same. So this is just extension. Okay, in this case, we have discrete, we have discrete external torsional moments. Now instead of that, we have smoothly distributed torsional moments. Okay, so let's talk about how we generalize this equation for the for this case. So as I told you, the total amount of angle of twist is sum of the contributions of small angle of twist, isn't it? So here we already discussed same thing here. Look at this. I told you that what summation can be approximated to can be generalized to integration. So if you consider very small points, okay? The same here. Instead of talking about a finite segments, so if you consider infinitely small size of segment, then the summation can be approximated to, not approximated, sorry, it is generalized to the integration. For what? For the all lengths, okay, all lengths. So here, the total angle of twist is integration of small angle of twist. But angle of twist, the angle of twist is a function of coordinate. That's why we need to integrate the derivative of angle of twist over the length of the segment. And that is the derivative of angle of twist with respect to coordinate was defined as the rate of twist, isn't it right? And here the rate of twist from the torsional formula, this is nothing but the internal torsional moment divided by the shear modulus and the polar momentum inertia. It is really straightforward. Then what is the solution procedure? The solution procedure is you have to calculate the distribution of torsional moment using the force equilibrium condition. So once you calculate the internal torsional moment distribution over the x-axis as a function of x coordinate, then you just integrate torsional moment divided by the shear modulus and then the polar moment of inertia for the section. If you consider just the constant cross section, then you can take out the shear modulus and then the polar moment inertia to outside. Okay. Now what if, let's consider an example. As an example, so let's consider this problem. Say, how do I say? And then it is subject to some torsional moments. So in this case, the characteristics of cross sections changes. Isn't this is part 1 and part 2, isn't it? Part 1 and part 2. So here, the total amount of angle of twist, the integration of the angle of twist for part 1, and then its integration for part 2. So we have to do this separately, okay? So instead of using this one single term of integration, okay, we need to split the integration into two parts, okay, two parts. Okay, let's solve one example here. So I have a solid steel shaft. This example is given in the textbook. So I have a bar, and then the bar is subjected to three different torsional moments, and we have to determine the maximum shear stress in each part of the shaft and the angle of twist between gears B and D, okay? Look. So here, if you example problem, and then first we have to idealize, isn't it? So I want to use the this coordinate system, and then we want to consider three different load. The first one is T1. So let's use double-headed arrow because it's easier to recognize its direction. This is external torsional moment. And how about T2 here? T2. T2, okay? And then I have T3. So let's check the force equilibrium. Sum of all the torsional moment in this direction should be equal to 0. So make sure that these are external torsional moment, okay? These are external one. So don't be confused with the external torsional moment and the internal torsional moment. Since we use the same notation, so it's quite confusing. But here, you know, where is it? The torsional moment is given in this equation. It's not an external one, okay? That represents the internal torsional moment. Okay, this is internal, and this is external one. Okay, let's go back to example problem. Then T1, and then because of its direction, minus T2 plus T3 is equal to 0. Okay, let's check. T1 was equal to 275. T2 is equal to, how much is it? 452. Sorry, this is Newton meters and Newton meters. T3 is equal to 175 Newton meter. So if you check this, the force equilibrium is satisfied. By the way, the force means, you know, force include both the real force and the moments, okay? So we'd like to represent the external actions. All right, so because we have this, and then let's try to consider the change deformation, not the change, sorry. Point A and B and C and D. Okay, and the E. And then look at this. So force equilibrium is satisfied, okay? So it's kind of is in equilibrium. So which means that here we can introduce a boundary condition to simplify our calculation. Let's say I want to choose point B as a reference point. If you do that, so we can prescribe the distribution of angle of twist here. So angle of twist look like this, okay? This is angle of twist. So here at this point we have pi B and the pi C and the pi T, okay? So make sure that the change of angle of twist of BC segment is equal to pi C minus pi B. But make sure that because of boundary condition, pi B is equal to 0. This is pi C. And then this is the angle, change in angle of twist in CD segment is equal to pi D minus pi C. So the reason that the order of these quantities is because of the choice of this coordinate system. That's why, okay? So once we have once we define the change in the angle of twist of individual segment, we are ready to calculate the internal torsional moment, isn't it, right? So internal torsional moment is, we can calculate the internal torsional moment using the force equilibrium. So T BC is equal to what? The length of BC segment and the shear modulus, and then the polar moment of inertia of the section. And this is delta PBC. This is equal to GIP, length of BC segment, and VC. And then internal torsional moment of CD segment is what? CD segment is equal to GIP, length of CD segment, and then this is VD minus VC. Then the remaining step is really straightforward. Okay, so we have to apply, there is it. So T3 and then T2 and then T1. So we can apply the force equilibrium for the individual nodal points. So for example, here if you do that, then we have external torsional moment, And then we need to consider internal torsional moment. So do you remember last time I told you that we're gonna use a right hand rule? So if you use a right hand rule, it's a stretching direction, okay? The stretching direction. Then the direction of my internal torsion moment look like this, okay? This is positive TCD. So which means TCD should be equal to T3. Okay, this is the first equation. And then we have two unknowns. We have another equation. Now let's check BC here. Where do you, for example, let's check here. So if you do that, we have one external torsional moment, and then I have one internal torsional moment, TBC. Sorry, no. Where is it? TBC. Yes, TBC. Okay. So then because of force equilibrium, TBC is equal to T1. So we can determine here from this, we can determine VC value very easily. So once we finish determine VC, then plug in VC into here, then to determine VD. Clear? Okay. Okay. So here, let me stop the second section of this lecture note. So let's take 10 minutes break before we move to the new section for the discussion of stress and strain in the torsional problem. Okay.